Okay, so before we start, are there any questions from the last day? We can start with a few discussions if anybody has any
Yeah,
questions.
yeah, it will always be nice if we can pick up some questions from the last session. Actually, this is the third day, second lecture.
Mhm.
So we are on the seventh lecture of the workshop. So it's nice to have some discussion at this point, and then Professor Dasgupta can take it from there. Participants are requested to put forward questions. I mean, if you have any.
But they may not have any. That's fine.
That's true. That's fine, but let us make sure that there doesn't have any.
Okay, let's make sure of that first. So if anybody has any questions, you can unmute and ask. If not, we will wait for a couple more minutes and for the people to join, and then we will start.
Hello, excuse me, sir.
Yeah, go ahead.
Sir, I have this paper on non-abelian discrete symmetric group from some Chinese authors, and in that group theory introduction, there is a definition of finding the order
Sorry, finding
class
what?
and
Finding what?
order of a conjugacy class.
Sorry,
Order
didn't get you. Finding the order of
of a
what?
conjugacy class.
Of what? Sorry.
Conjugacy class, sir.
Yeah, true.
So, what does it mean? I mean, the order.
I'm not very sure that unless you, because these words are used in different meanings, but typically order of a conjugacy class would simply mean how many elements a particular conjugacy class has.
Okay.
Say, for example, the identity would have only one,
Yes.
always, in every group. But
Okay.
there would be several elements. Say in the example that we talked about, S3 or our
S3, yes.
example of the equilateral triangle, you had one conjugacy class with one element, one with two, one with three.
Yes, sir.
And typically, say the number of conjugacy elements in a conjugacy class, for example, in Sn, the permutation group, for that there are nice combinatoric results. That is, you can easily figure it out from the fact that every cycle stands for a conjugacy class, and you just have to ask how many cycles can there be.
Okay.
So this, of course, depends on the particular group. Now, I'm not sure whether that is the sense in which this is being used here, but that usually would be the meaning.
Okay, sir. Here they do the, I mean, the after how many multiplication do we get the identity?
Oh, that's
like that here?
okay. So that is a slightly different thing. That's really not the order of the conjugacy class. That's the order of an element.
Oh, okay. Sir.
Okay.
Oh,
So
yeah.
basically, that's one topic which I actually did not talk about, but it's a
Okay.
pretty straightforward thing. The idea is, at least if you have a finite group, if you start with an element of a finite group and keep on multiplying it by itself, so you get a square, a cube. That is, a square, of course, means a times a, and so on.
Yes.
And you keep on doing this. Of course, you can't go on forever, right? Because
Yes.
this is a finite group. You have only finitely many possibilities. So
Yes.
after a while, you must repeat. And from that, you can show that because of this basic group structure, you can show that this will automatically mean that some power of every element, in a finite group at least, start with any element. If you keep on raising it to a power, succeeding powers, you must hit the identity.
Yes, sir. Yeah.
And the smallest value for which you hit the identity is called the order of that element.
Element. Okay. I thought it is the order of the class and like the. Okay, sir. Thank you, sir.
Okay. By the way, you should also realize that it's also the order of the class in the sense that every element of a given class should have the same order.
Okay, sir.
And that's pretty easy to figure out. Just simply go by the definition.
Thank you, sir.
Order, in a sense, is a class function. In fact, we will meet a very important class function today in today's lecture. Okay, let me start the formal lecture now. If nobody else has any other questions. Okay, let me just start by the presentation then. Yeah. So I hope everybody can see this. It's visible, right? The slide?
Yes, sir.
Okay. So this is where we left off at the end of the last class, more or less. We showed that for an arbitrary z, just let me remind you of what was at stake. Ultimately, oops, this is actually not that. It's a long way beyond that. Okay, so let's go back to where we were. Okay, so this was where we left off. This is the so-called great orthogonality theorem, at least in terms of components. And just to remind you what this is, for a given group, and this is for a finite group for the time being, as I said, the sum over a group can always be extended to an integral over group elements, provided you have some other restrictions like compactness, etc. For the time being, let's stick to finite groups. In a finite group, you will have a certain number of irreducible representations. We will soon be able to figure out how many. And what you have done is you have labeled the irreducible representations d1, d2, d3, and so on with this square bracket, this round bracket alpha on top is just a label for an irreducible representation. And you have put up the convention that a particular equivalent representation will only be, or the entire equivalent class of representations will be counted only once. So if one irrep is counted, any equivalent irrep will not be counted. And if you do that, then you have this labeling d alpha, d beta, and so on. And this is a statement right now about the matrices, about the irrep matrices. If you take the irrep matrices, take the I primeth element and J prime jth element. Notice that I prime, J prime j are all free indices. They're not being summed over. But you do this, take the alpha's I primeth element for the element G, the beta's J prime jth element for G inverse, and multiply them together. These are just numbers, so you're just multiplying them together. And then sum up over all the group elements. You end up with something which is almost always 0. It's not 0 only when alpha is equal to beta, I is equal to j, I prime is equal to j prime. And if all that happens, then the value is mod g by d alpha. This is the orthogonality theorem, at least in the component version. This is where we ended last day. And as we said, most of the results, at least in group representation theory, essentially can be derived straight out of this one. Okay, there's one thing, as we said, most finite groups do have unitary representations. And in fact, they always have unitary representations if a group is finite. But all representations are not unitary, but they are equivalent to unitary representations for a finite group. If you have a unitary representation, of course, then the matrices that you are getting are also unitary. And that means that this inverse matrix is actually the adjoint of the matrix for G. And because of the adjoint, you have a complex conjugate here, and also J prime J becomes JJ prime. So this is for a unitary representation. Okay? But this is not for all representations, but since all finite groups, for all finite groups, you do have a unitary representation equivalent to any given irrep, even any given representation, by the way. It doesn't even have to be an irrep. Then instead of, when I'm labeling the irreps, I can always choose a unitary representative. If I do that, this is the relationship I get. Doesn't look like a huge difference, but notice that this is for a different matrix. The two matrices here are different. One is for G, the other is for G inverse. Here you have matrices both for G multiplied together. Now the next step is to simplify this equation a bit further, in the sense that this has way too much information. There are many equations here, one for each I prime, each j prime, right? So in order to simplify this further, or reduce the amount of information that the equations have so that they become easier to work with, what we can always do is do this. If you put I equals I prime and j equals j prime, then what are you going to get?
Delta alpha beta.
What about the right hand side? It becomes delta alpha beta. If you put I equals I prime and j equals j prime, remember, I'm not putting I equal to j and I prime equal to j prime. I'm putting I equal to I prime. That is, I'm putting these two indices the same and these two indices the same. So what will this product become? Do I put I equals I prime and j equals j prime?
It will become delta I.
I hope this is visible.
Delta Ij.
It becomes simply delta Ij. Right.
Delta Ij.
It's delta Ij times delta Ij, which is of course just delta Ij. Now, next, but what happens to the left hand side? If I put I equal to I prime and j equal to j prime, what am I getting on the left hand side?
Trace of the representation.
Well, not really. You're getting the diagonal element, one diagonal element each. To get to the trace, that of course is what the next step that I will do, which is sum up over all I and sum up over all j. Then you get the trace, right? It's not just enough to get a diagonal element, you have to add up all the diagonal elements. So basically what I'm going to do now is put I equals I prime, j equals j prime, and then sum up over both I and j. Then what will happen? Okay, can anybody tell me what happens to the left hand side then? The full thing. Full left hand side, what does it read now? I am putting I equals I prime, j equals j prime, and summing up over all I, all j, whatever is on the left hand side. Notice that there are three sums here. One is the sum over g, and then we have sums over I and j. But I am summing dii alpha g over I and d beta jj g star over j. So what is the product that you get? on the left? Okay. Just need to check whether I'm still connected. I hope I'm connected. Yeah, I'm still connected. So what happens to the left hand side? This becomes chi alpha g, the character or the trace, right? And this becomes chi beta g star. So this is sum over all g, chi alpha g, chi beta g star. Okay? What happens to the right hand side? If you put I equal to I prime, j equal to j prime, sum up over I, sum up over j, what do you get? That's a pretty straightforward thing, right? You have already told me what happens when I is equal to I prime and j equals j prime. The delta ij, delta I prime, j prime just becomes delta ij. Then you are going to add it over I and j, both. What will you get?
So sum delta ij. So I will run from 1 to n and j will run from 1 to n.
N, well, actually, I will run from 1 to d alpha and j will run from 1 to d alpha. The dimensionality of the matrices. Actually, d beta, but doesn't matter. Yeah, unless alpha and beta are the same, it vanishes anyway.
Sir, I have a confusion on that. So alpha is a hanging index, or I mean, alpha is a dummy index on the right hand side, or what should I take? Alpha?
No, does it look like a dummy index to you? It's not, right? Alpha, beta, in fact, as it's written, all the indices, alpha, beta, I prime, j prime, all of them are free indices. Alpha, beta, of course, have a different role than the other indices. Alpha, beta are just labels for the particular area, but they're all free.
Okay.
Yeah.
I thought alpha is a repeated index. I saw that's why there is a sum in the right hand side.
No. There is no repetition or anything. Of course, if alpha is not equal to beta, then both sides are zero anyway.
Okay.
So the simple question I have for you is, now I am going to make them into summation indices. I will put I equal to I prime, j equal to j prime and add up. So what you will get is this becomes chi alpha g, this becomes chi beta g star, and the whole thing is summed over all group elements. On this side, delta alpha beta will still remain, mod g will still remain, that's the number of group elements. But this becomes delta ij summed over I and j, where I and j take all possible values, means 1 to d alpha each. So what is the sum? In other words, what is this sum? Sum I equals 1 to d alpha, j equals 1 to d alpha, delta ij. How much is this?
So it will be like one square plus.
1 square. Where do you get the 1 square? Of course, 1 square is 1, but
Plus.
why do you use the square? I don't understand the square. You did have delta ij, delta I prime, j prime, but that has become delta ij square, which is actually delta ij, right? Delta ij square is of course the same as delta ij, right? It's 1 when I is equal to j and 0 when I is not equal to j. But now what is this sum? Okay, let's just do it one at a time.
D alpha
Is what?
D alpha.
It's exactly d alpha, right? Because if you do this sum, how much are you going to get? J runs from all possible values. At least one of those, in fact, exactly one of these values will coincide with I, whatever the I is. So this sum has to be exactly equal to 1, because for this sum, for all values of j, you get 0 except for one value for which you get 1. So this sum is 1. And then you are adding up a lot of bunch of 1s. So you have to get d alpha. Right? So basically when you do this, what happens is that d alpha in the denominator here cancels out. And you end up with a final result which is rather simple and also quite sprightly. You just get this. Sum over all group elements chi alpha g, chi beta g star is simply mod g delta alpha beta, where chi g is nothing but trace of dg, the character In fact, we had already introduced this before, but this is the first time the character is really entering into our discussion properly. The reason why we are interested in the character is primarily because of this. It has this very nice result, which is called the orthogonality relation of characters. And why I call it an orthogonality relation, well, it should be sort of obvious, but if it's not jumping out in front of your eyes, let me just point out this is really something like this: chi alpha G1, chi alpha G1 conjugate, or chi beta G1 conjugate, right? That's what G1. Then you have chi alpha G2, chi beta G2 conjugate, and so on. How many such terms you have? One for every group element. And the result is mod G delta alpha beta. Now, what should jump out to your eyes immediately is that if you thought of a vector like this, a row vector or a column vector, right now I'm writing it as a row vector because it's easier to write that way. Suppose you defined a vector like this. Took every character for every group element. So if there are mod G group elements, there will be G mod G at the end. You take every one of these characters and make a row vector out of them. That's a mod G the dimensional row vector. So what does this tell you about such vectors? If you have two such vectors, one for the irrep alpha, another for the irrep beta, what is this telling you? This product that you have is nothing but a standard dot product, right? When you take a dot product of two complex vectors, what do? You conjugate one and multiply by the corresponding element of the other and then add up, right? You do know this, right? This is the form that the dot product has for complex vectors.
Yes, sir.
This is basically, of course, something which you all know, because in quantum mechanics you do it all the time. This mathematicians actually call it the Hermite product and not really the inner product. But for a physicist, this is usually what we call the inner product, right? So what is this telling you? It's telling you that if you form vectors like this, then these vectors, and you form one vector for each irrep, then these vectors are going to be orthogonal to each other. Right? If you take the dot product, you're going to get 0 unless alpha equals beta. So can you tell me what this tells you about the number of possible irreps? What is the dimensionality of these vectors that we have written down?
The number of the group elements.
Right now it's the number of the group elements. That's what we have written down. So now tell me, from the fact that these for each irrep you have an orthogonal vector, what does it tell you about the number of possible irreps? Does it tell you anything at all? How many irreps you can have? How many representations you can have? The answer is infinitely many. The question is how many irreps can you have? Of course, not counting equivalent irreps as separate ones, only counting equivalent irreps once. How many irreps can you have? I'm not asking for the number, but does this tell you anything about the number? I'm not asking about the exact number. Okay. How many orthogonal vectors do you have in ordinary 3D space?
3.
3. Why can't you have more than 3?
Because I can express all the vectors by this 3.
Okay. The actual reason, well, you're right, but the actual reason would be that you cannot have more than 3 linearly independent vectors in a 3D space, right?
Yes.
And orthogonal vectors are definitely linearly independent.
Yes.
So what does this tell you? At least at this stage, what is this telling you is you cannot have more than mod G irreps, right? Yeah?
Right.
So at least one thing you can see, if it's a 6-element group like our S3, you can't have more than 6 irreps. Doesn't mean that you have 6 irreps, It just says that you can't have more than 6. In fact, actually, you will soon see
It
that you
says
have
the
less.
upper limit of the.
This is an absolute upper limit. Okay. Actually, you will soon see you will have less in general. Okay, so let's see why. So this chi is called the character of the representation. It's a map that we are talking about. It maps every group element G to this trace of DG or chi G. Now, one important thing, we derive this result using the unitary representation, right? We started from this unitary version and then put J equal to J prime and then added up. That's why you had both G and G star and not G and G inverse, right? But remember, for every finite group, no matter which irrep you have, you must have an equivalent unitary irrep, and the trace does not depend on, it does not change when you do a similarity transformation, which means the trace of every irrep is the same as the trace of the corresponding equivalent unitary irrep. As a result, this result, although it was derived for the unitary irrep, is actually valid for all irreducible representations. Is that clear? This result, of course, does not work for all irreducible representations. It works only if you are using unitary irreps. But even if your irrep is, whether your irrep is unitary or not, the character is the same. So as any result about the character will be the same no matter whether you are using the unitary irrep or any irrep. So the result, the theorem that we had is that every representation has an equivalent unitary representation for a finite group. That becomes very important for us here because it allows us to say that I don't care which irrep you have, whether it's unitary or not, this orthogonality relation will always hold. Okay. Now comes a very important reason why classes, we talked about conjugacy classes a lot, right? But why are classes so important in representation theory? Well, you can see that the thing is very simple. If two group elements are conjugate, if G and G prime are conjugate, that means there exists some G bar in the group such that G prime is G bar G, G bar inverse. And of course, that means that the representation for G prime, the matrix DG prime, is going to be DG bar, DG, DG bar inverse, because representations always mimic the group multiplication law. But now what do you know about DG prime and DG, these two matrices? What does this tell you about these two matrices? If G and G prime belong to the same conjugacy class, that is, they're conjugate to each other, what connection do we get between their matrices?
A similar matrix.
They are similar matrices. And in particular, if they are similar matrices, they must have the same character, right? So if G and G prime are conjugate, then the characters must be the same. And this means that character is a class function. It depends only on which class the element belongs to, not the actual identity of the group element that much. Every element in a class has the same character. So I don't have to say, for example, our S3 group, I don't have to ask what is the character of A, B, C separately. Give me the character of any one of them because they're all in the same class. The moment I have the character for one of them, I have the character for all of them. Okay? So what this means is that instead of summing up over all elements of the group, which we were doing a while ago, you can actually sum up only over classes. That is, instead of saying chi alpha of G, you can say chi alpha of C1, chi alpha of C2, chi alpha of C3, and so on. One character for each class. The only important thing you have to remember is that you have to put in an extra factor of NCI here, where NCI is nothing but the number of elements in that particular class. Is it okay with everybody? All I'm saying is, if you just count all the elements in a particular conjugacy class, they all will contribute exactly the same amount. So instead of summing up over all elements, we just sum up over classes, remembering to weight each class by the number of elements in the class, I will definitely get the same relationship. Is this okay with everybody? So just to perhaps make this a bit more clear. For our example of S3, remember we had three classes. C1 was identity alone. C2 was the two rotations, non-trivial rotations DNF. C3 was ABC, the three reflections. So what we had right now is basically the sum which goes like this. Okay, let's forget about the sum. Let's write it out in full. Okay, that may be a bit boring to the people who have already understood this, but it might help. So what we were saying right now is something like this: chi alpha E, chi beta E star, plus chi alpha A, chi beta A star, plus chi alpha B, chi beta B star, and so on and so forth. For all the 6 terms, this was delta alpha beta into mod G, which is of course 6. But what you can do is, instead of summing up over group elements, as was done here, you could just say chi C1, chi alpha C1, chi beta C1 star, plus chi alpha C2, chi beta C2 star, times 2, because C2 is of course DNF, there are 2 of them, and 3 of ABC, and for each of them you get the same contribution. This is also equal to 6 delta alpha beta. Now what does this tell me? This actually tells me that instead of having a 6-element vector with chi alpha E, chi alpha A, etc., we could also think of this vector, chi alpha C1, and just to make it look even more like our ordinary normalized vectors, we could just use this. Sorry, chi alpha. If I are talking of the alpha theorem, this will be chi alpha C3. Now, if you form such a vector, one for the irrep alpha, another for the irrep beta, and call this, say, the chi vector for alpha. Bad handwriting, but then chi vector alpha inner product with chi vector beta is simply delta alpha beta, right? I've got rid of all the factors of 6, 2, and 1 because I've just absorbed them in here. Is this okay with everybody?
Yes.
Okay. Can anybody now tell me, what does this tell you about the number of possible irreps? How many irreps can you have? Is that going to change your opinion about the number of possible irreps?
It would be one irrep corresponding to each conjugacy clause.
Well, that's the final answer, but that doesn't follow from this. From this, what follows is simply this: number of irreps is less than or equal to number of classes. Right? Because all you have said is corresponding to each irrep, you have an orthogonal vector, and the dimension of the space is nothing but the number of classes. So you cannot have more than the number of classes. So things get even more restricted. Our S3 had 6 elements, but only 3 classes. So it can have only 3 irreps, no more than that. Okay. Remember, why are irreps so important? All representations are built up out of irreps. You take small copies of irreps multiple times, and you build up your representation. Okay. Right? So if you understand irreps, you understand everything about all possible representations in a sense. And we will soon see irreps have deep physical significance. So having said that, this result, which says that if you know the number of classes, that puts an upper bound on the number of possible irreps, is a very important result. In fact, what you said a while ago, sorry, hello?
Yes, sir, we can hear you.
No, sorry, I am getting a call. So, okay, so I'm back. So, right now what we have shown is the number of irreps is bounded above by the number of conjugacy classes. But what is also even more interesting is that this is like an ordinary dot product, especially if you introduce this vector, where you have one element for every class and you weight the character by the square root of number of elements in the class by the number of elements in the group, then you will simply get this result, right? For two irreps, chi alpha dot chi beta, where this dot means the complex conjugate and sum up over components dot, you simply get delta alpha beta. The mod g and everything has been taken care of by essentially putting them in the factors here. Now, if you have orthogonal vectors, what's great about having them? It's easy to see that you can pick up components simply by doing a dot product, right? If you want the x component of an arbitrary vector, all you have to do is take a dot product with I. If you want the y component, you take a dot product with j, and so on. Exactly the same mathematics will work here. So right now we have a bound, and although I do have the proof in the slide that number of irreps is exactly equal to the number of classes. What that means is, if you have any class valued vector, that is a function which takes one value for every class, so then any such function can always be represented as a linear combination of these irreps. That can be proven. The proof is slightly lengthy. I'm just omitting the proof. That really means that not only are the irreps independent, they also span the space of these class vectors, and that means the number of irreps is exactly equal to the number of classes. So S3 has exactly 3 irreps, or to be more precise, 3 inequivalent irreps. Okay, now let's come to the question that we have been asking for a long time. Suppose you have a reducible representation. Can you find out how many times each irrep occurs in that? And that's a very important question physically. Why? I will indicate later. But this, even at a mathematical level, this is an interesting question. How many building blocks go into making up a particular reducible representation? Just to remind you, if your representation was built up by smaller representations, you started with the smaller representations and build them up, you will get a block diagonal form. And if you get a block diagonal form, then this is obvious to you, that how many times each irrep occurs. You can just see it from the block diagonals, blocks. However, as I said before, that would happen only if you chose the basis properly. If you had mixed up the basis, if you had used some other basis, then the block diagonal form is not apparent. So for a general representation, there are two important questions. Is it reducible at all? And if it is, what is the reduction? How many times does each irrep occur in it? So let's answer that question. So reducible representation can be thought of symbolically of this form. That is, you can build it up out of m alpha copies of the irrep d alpha. Of course, a given irrep can occur multiple times in a representation. So maybe a given irrep occurs 3 times, another one occurs 4 times, and so on. And you have built up a big representation using that. The question I have for you right now is how do you find out m alpha? And the answer to that is as follows. You may not have a direct sum like this. That you will have only if you can see the block diagonal structures. But you will always have something like this. That is, there should be a similarity transformation possible, which will change whatever DG you have, all the DGs, to the same block diagonal form. Okay. Now, what does this tell you about the character? If you are in the block diagonal form, then it's easy to see that since every one of the representative matrices are sitting right across the diagonal, their diagonals are of course the diagonals of the actual matrix, big matrix, right? So if you have these small blocks which are all sitting right across the diagonal, then the actual diagonal, the full diagonal, is made out of the diagonals of these. So if you want the trace of that matrix, at least in the block diagonal form, you will simply get the character of the alpha irrep times how many times that irrep occurs. Is this clear to everybody? Yes? No?
Yes, sir. It is clear.
No, of course, the question really is addressed to people who might want to say that they have not understood. If they have not, if nobody says that, I'm going to assume that everybody has understood. Okay, fine.
So,
This is, yeah.
sorry to interrupt you, but I'm just confused about one thing. We are establishing the orthogonality of in what space over here?
In a space of, in a space of, space which is isomorphic to Rn, where n is the number of classes. Or you could just say space of row vectors with number of elements equal to the number of classes. That's a space. Remember, in linear algebra, ultimately all spaces of the same dimensionality are actually isomorphic to each other. So as far as linear vector space structure is concerned, it doesn't really matter what space you're talking about. You have 3 elements. 3 components is a 3-element vector space. It's a 3-dimensional vector space. You have 5 components, it's a 5-dimensional vector space. And the space really is a space of class functions. Functions whose values depend on which class the element belongs to. A function from the group to the field, say from G to R or G to C, actually G to C is more appropriate. But it's not really a function on the group, it's a function on the classes.
So we are expanding every representation in a basis of the irreducible, in the basis consisting of the irreducible representations. Right?
Well, actually, that we covered in the other day. What you're doing is if you started by building up, if you had a lot of small irreps and you formed a direct sum vector space and chose the basis vectors to be essentially the basis vectors of each irrep, then you will end up with a block diagonal picture. But for the big vector space, you can always choose some other basis. Don't confuse that basis with the orthogonality that we talked about. That was in the class space. Here is some big representation. It could be 40-dimensional. I could have put in many different representations together. Maybe I will just remind you of the picture that we had. Say what I can have is maybe I have a 2-dimensional irrep with 4 elements, and that is sitting, maybe 3 copies of that is sitting on the diagonal of my representation, and maybe I have another 4-dimensional irrep for the group, and only 1 copy of that is sitting along the last block of the diagonal. So if you have this 3 copies of the first irrep and 1 copy of the second irrep, let's say. So what will be the dimensionality of this representation? Or just think of the matrix. What will be the size of this matrix?
It will be 10 cross 10.
This will be 10 cross 10 because 3 times 2 plus 1 times 4, right?
So it's a representation on a 10-dimensional vector space.
In this case, it's a representation of 10-dimensional vector space. So for our example of molecular vibrations for a square molecule, you had an 8-dimensional vector space on which you could get a representation of the group of symmetries of the square, right? You could actually build up bigger and bigger representations anyway, depending on what kind of systems you're talking about. Say even for the square, if you're talking of motion in 3 dimensions, then it will be a 12-dimensional vector space, really, right? 3 components for each of the 4 atoms.
Here, one comment I can say that
Yeah.
the whole vector space is split into 4 invariant subspaces actually.
In this case, yes.
Um,
Yeah,
right.
for this example, yes.
Okay.
But look, the block diagonal structure will show up only if you chose your basis in such a way that these two, say, the first two basis vectors were actually basis vectors for this invariant subspace. The next two were basis vectors for this invariant subspace. The next two, E5, E6, were basis vectors for this invariant subspace. And then E7 to E10 were basis vectors for the last invariant subspace. Only if you do choose your basis vectors correctly will you get this block diagonal structure. Or correctly meaning luckily or correctly depending on what you want. But in many situations, your basis vectors will not be that, it will not be obvious what basis vectors to choose to get this reduction, right? It might very well be that you're using E1 plus E3 and E2 minus E4 and such things as basis vectors. Then you will no longer see a block diagonal structure. Then you will see something which is not block diagonal at all. Okay, the block diagonal structure shows up only if you use proper basis vectors, or if you're lucky in your choice of basis vector.
Yes, so this part I'm clear, but we also
yeah.
spoke of another space that has a dimensionality equal to the number of conjugacy classes.
Yeah, that's an entirely different thing.
Yes,
that
sir.
basically that is simply this. You take the characters, and the characters depend only on the classes, so you don't have one character for every element, you just have one character for every class. So C1, C2 up to CNC, where NC is the number of classes. Okay, and form a vector with that. Or if you want to make it even neater, you throw in factors of square root NC1 by mod G and so on with every one of these, so that the dot product actually ends up looking exactly like the ordinary dot product that we do. We don't even have to worry about weighting factors. But that's just making it look a bit neater, nothing else. In that space, okay, that's a different space altogether.
This spans which space? What are the members of this space? Are they all? This is the space of representations.
No,
Of a
representations don't. This is just a space of ultimately this is a space of class functions. As I said, suppose I have a function from the group to complex numbers, where the function, of course, if you say function, every group element should have a value, right? A function should match every group element to a complex number, right? But if your function happens to be a class function, which means it takes a value which is the same for every members in the class, just like characters, but any class function, okay? If you have that, then what will happen? Then you will get these numbers FC1, FC2. So the function is described essentially by a bunch of numbers like this, right? If you know these numbers, you know the function completely, right? You agree?
Yes, sir.
And you can think of this bunch of NC numbers as a vector, right? You can always do that, but bunch of phone numbers you can always treat as a vector in a vector space. That's what we have done. So this vector space has nothing to do with the space on which you're talking of representations. It's just another vector space which has come about in the calculation. Okay? But what we have found out is the character vectors are orthogonal in this vector space. So it has to, the number of such character vectors must be bounded by the dimension of this space, which is just nothing but the number of classes. Is that clear?
Yes, sir. Okay. Now it's...
Okay, so let's move on quickly to the useful results, which is this. This result that chi g is m alpha chi alpha g. Of course, this will be obvious if you look at what I wrote down here, right? To get the character, for the entire matrix, what you will do is add up the diagonal elements, right? But what are the diagonal elements for this block diagonal version? It's just nothing but the diagonal elements of individual irreps, right? So if you add these two, you get the character of the first irrep, and you get that 3 times because that's occurring 3 times. And to that, you're going to add the character of the second irrep. So the character for this particular matrix will be 3 times chi1 plus 1 times chi2, right? Just the character times the number of times the representation occurs. Remember, this is chi-g, this is for 1g. The point is, if you have a block diagonal structure, you will get the same block diagonal structure for every one of the group elements. And so this will follow. Now, the important thing is this will follow no matter whether you have got the block diagonal form or not. Even if you have not got the block diagonal form, the very fact that you can block diagonalize it by finding some similar transformation is enough to say that this is going to work, right? Why? Because ultimately, because character, which is a trace, does not change with the similar transformation. So whether you do the similar transformation or not, whether you have the block diagonal form or not, chi-g will always be this sum. Okay. Can you now tell me how to find out M alpha from this? If I knew the assumption is I know all the characters of the irreps somehow. If I know that, can I find out the number of times an irrep occurs in a representation? All you have to do is, well, notice that this chi-g is simply M alpha times chi alpha vector. So chi-g is M alpha chi alpha, g means the chi vector that we wrote down. The class valued vector is just M alpha chi alpha vector. And so from a linear combination of these class valued orthogonal vectors, I want to find out what is the coefficient of chi vector alpha. How would we do that?
The normalizing orthogonality condition.
Yeah, basically what you would do is, suppose you had 3 vectors A, B, C which are orthogonal to each other. And you had a vector like this. You want to find out alpha. How would you find out alpha? Suppose you know A, B, C.
Dot product with A.
You just take the dot product with A, right? And if they're orthonormal, even better, then you will just get alpha. You take the dot product with B, you get beta, right? If they're just orthogonal and not normalized, then you will have to take care of the fact that A dot A is not 1. You have to put in that factor. But other than that, your job is done. Is it okay? So that means just by using that, now that you have orthogonal vectors, all you have to do is you will take the dot product with chi alpha of chi. All you are doing is taking dot product of chi alpha with this, which of course has to be, now the alpha has to be changed to beta because this is a specific alpha, this is a dummy index of summation. But then this is just m beta, the number, then chi alpha dot chi beta. And what is chi alpha dot chi beta? That's delta alpha beta. So this is just m alpha. Okay. So all you have to do is take the dot product with the corresponding vector chi alpha. Okay, so the number of times an irrep occurs in a representation can be determined by simply doing this. Or if you go back in terms of class characters and not just in terms of these vectors, all you have to do is multiply the character that you have by chi alpha ci's conjugate, weighted with the factor nci. These were taken care of in the square root nci by mod g, which were there inside the definition of the vectors. But if you don't want to look at the definition of the vectors, just go by the characters, which are just numbers, you have to just do this. And that will give you m alpha. Number of times a particular irrep occurs. Simple, you just find out the character of your representation, you multiply by each class's value by the conjugate of chi alpha star ci, weight with the number of elements the class has, add up together, and whatever you get, divide by mod g, you've got m alpha. That's it. I'll just use it soon and you'll see that this is pretty easy to use. So how many times a given irrep occurs? You can immediately find out either by using this version, which is the sum over classes, or this version, which is the sum over group elements. Essentially, they're exactly the same expression. Just this one uses the fact that every member of the class contributes the same value, so you're just weighting by the number of elements the class has. Okay. what is the criterion for irreducibility now? That's the next point. Given a representation, you will look for reduction provided it is reducible, right? But how do you know that a given representation is irreducible or not? Even the answer to that is also pretty easy. If it is reducible, it's of the chi j will be of this form, or chi vector will be of this form. And if it's an irrep, even then it's of this form, right? If it's an irrep, then only one of the M alphas will be exactly 1, because that irreducible representation occurs once, and all other chi's, all of the M alphas will be 0, right? Because the other irreps will not show up. Now, if you take the dot product of this chi with itself, chi dot chi is of course chi alpha dot chi alpha, that will be 1. Now, I will leave this as the homework. It's a very trivial calculation to do. Basically, just use ordinary vector dot products. That this actually happens to be both if and only if. I have shown that if chi is an irrep, chi dot chi is 1. Then the theorem is also only if chi dot chi is 1, then chi is an irrep. That's the criterion for irreducibility. All you have to do is take the dot product of chi with itself and ask, is it 1? And if it is, then you have got an irreducible representation. If it's not 1, you haven't got an irreducible representation. So the proof I'm going to skip over. It's a straightforward proof. Do it as a homework. But this is the criterion. If chi dot chi is 1, it's irreducible. If it's not 1, it is reducible. Or in terms of class characters, what this chi dot chi means is you just take the chi c's, take the mod square, add up. Add up over all group elements, but of course, if you're adding up only over classes, weight them with the MCIs. And if you get mod G, you're done. Then it's irreducible. If you get a multiple of mod G, then it is reducible. Okay, now let's come back to our one representation that every group has. Everybody remembers this one, I hope. The regular representation, the one which we built using the group itself. So the question is, first of all, question is this reducible or irreducible? Actually, I already told you the answer the last day. But anyway, I know the characters, right? Chi regular G has to be mod G for G equals the identity, and is 0 for all others. Everybody remembers this, I hope. Now, this means if you take the chi regular vector and just take its mod square, that is, you take its dot product with itself, you have to add up chi regular G with chi regular G star for all group elements. So if you do that, you of course get only one term, that is for G equal to E. For everything else, you get 0, and you get mod G square. But is mod G square equal to mod G? Yes or no? Remember, the irreducibility criterion is that this chi dot chi should be mod G. Is this equal to mod G? Come on, the question is the square of a number equal to itself?
No.
No, unless you are dealing with a one-dimensional group. If you have a trivial group which has only one element. For all other groups, mod G square is of course more than mod G. It's also a multiple of mod G, which is good because if it had, the proof a while ago would have shown you that it has to be a multiple of mod G. But anyway, this shows that this is reducible. And if you want to find the reduction, what do you do?
Mod G is actually order of the group.
Order of the group, right?
Right.
So mod G square can be equal to mod G. Mod G, remember this being equal to mod G equal to 1 is the criterion, but that's okay. I made a mistake here. This is not really mod G square. This is mod G because you have to divide by 1 by mod G. So there's a typo. This chi regular mod square, if you take the vector and mod square it, you get mod G. But you should get 1. Or perhaps it's easier to think about it in terms of this. Sorry. Chi G. Okay, what I really mean is this. take chi G, take its mod square, and sum over all group elements. The criterion of irreducibility is this should be mod G. Okay, if you did that for our regular representation, you actually get mod G square. Why? Because only one term contributes, and it contributes mod G square. So these two are of course not equal to each other. This is the order of the group, this is the square of the order. And unless the order of the group is 1, which means it's a trivial group with only one element, you will definitely have a violation of the irreducibility criterion. So the regular representation is definitely reducible. Okay. And if you look at the M alpha formula in terms of sum over the group, is chi alpha G's conjugate times chi G. In this case, let's talk about the regular representation. So chi regular G, that is 1 by mod G. And can anybody tell me how much this is? Chi regular G, remember, has this very simple form. Chi regular G is
it should be equal to just G.
Mod G if G small g equals E, otherwise 0. What should it be?
It will be chi alpha E.
Chi alpha E, right. Because chi regular G has only one element which is non-zero, that's for G equal to E. And that mod G cancels out this mod G. But what is chi alpha E? The character for the identity elements representation. The identity element is always represented by the identity matrix. So what should this be?
Order of the
It is G.
Order
of the group.
No.
Order of the conjugacy clause.
No. Chi alpha, remember this is just, chi alpha is what? Chi alpha is a trace of a matrix, right? Trace of D alpha E.
E is your identity matrix.
E is the identity matrix.
So
Which identity matrix?
that the identity group element corresponds to identity group element.
Yeah, but which identity matrix?
Where it will be the
D
order.
The identity matrix of dimension of whatever space the irrep lives in. You're confusing when you say mod G, you're confusing this with the regular representation. This is not a regular representation. This is the irrep that we are talking about. Okay. The alpha irrep is on some smaller space, right? And the DE is basically the identity in that space. This trace is nothing but the dimensionality of the irrep.
Right.
So we have a very important result which says that the regular representation is special. I've already claimed that it's special, but now you see why it's special. First of all, M alpha is non-zero for all alpha. And M alpha that's the important thing. Every irrep occurs in the regular representation. Okay. If a particular M alpha were 0, then you would have said that in this particular regular representation, even if it's reducible, this particular irrep does not occur. But every irrep occurs here because all the M alphas are non-zero. And not only that, every irrep occurs exactly as many times as a dimension of the irrep. Okay. So every one-dimensional representation, there may be more than one-dimensional representation, but every one-dimensional representation will occur 1 times. So if these are 3 different 1D irreps, not the same irrep will only occur once. But if you have 3 irreps for that group, 3 1D irreps, they will occur 1 times each. Every 2D irrep will occur twice. Every 3D irrep, if you had a 3D irrep, will occur thrice. Every 4D irrep will occur 4 times. So that will tell you, okay, say for example, for this the dimension, for every, say take a look at these two. How many rows and columns does this give you? How many rows? You have a 2D irrep, that would give you 2 rows, but it's
4
occurring
rows
twice.
and 4 columns.
4 rows and 4 columns for this block. A 3D irrep will give you 3 rows and 3 columns. Right? But will be repeated 3 times, so it will have 9 rows and 9 columns. So if you add them all together, what you're going to get is, if you take all the irreps, say the first irrep has dimension d1, it's going to occur how many times? D1 times. So how many rows does that contribute? D1 square. You get that?
Yes.
The representation has d1 rows in itself, but it will occur d1 times. So it will actually contribute d1 square rows and also d1 square columns. The second irrep will contribute d2 square rows and columns. d2 for each block, but d2 times. And so on. So if you go all the way up to the number of classes, which is the same as the number of irreps, what must you get? This is the number of rows and columns. Rows and columns of what?
The
Regular representation, sir.
Yeah. So what should this be? How much? What? How many rows does the regular representation have?
Maybe mod G.
Yeah, it has to be mod. So you get a very, very interesting criterion. You see that d1 square, d2 square, if you add all the squares together of the dimensions, you must get mod G. Now this is actually a huge amount of information, so let us try using that. Let's try to see whether we can find out what can we find out about the irreps of our group S3. Remember, we had 3 classes: C2, which was only D and F, and C3, which were A, B, and C. So how many irreps does this have? How many irreps?
3 reps.
3 irreps. And what do I know about the irrep sizes? Well, what I know is d1 square plus d2 square plus d3 square. How much must that be?
6.
6. Good. Now you have three non-zero squares adding up to 6. Can anybody tell me what they have to be? d1, d2, d3. What are the possible values?
1, 1 and 2.
1, 1, and 2. Just think about it. That's the only set of 3 squares which add up to 6.
2 plus 2 plus 2.
No, 2 plus 2 plus 2 are not squares, right? d1 square, d2 square, d3 square has to add up to 6. 3 perfect squares which add up to 6. That's 1, 1, and 4. 2 plus 2 plus 2 is 6 is correct, but 2 plus 2 plus 2 is not a square, right? Is it okay?
Yes, I got it. 1 plus 1 plus 2.
Is 1 and 1 and 2. So 1 square plus 1 square plus 2 square is 6. So what I already know just from this count is that you have 3 irreps and the dimensionalities has to be 1, 1, and 2. So
Okay, sir.
Okay, this is here I am just using standard notation from crystallography. Frankly, I don't even go about memorizing these notations, so I don't really suggest that you do it unless you are going to study crystallography or this in some detail. But 3 irreps, they are called A1, A2, and E for crystallographic reasons more than anything. This is called the Mulliken notation. But A1 is the standard. Remember, 1D irrep every group has. What is that? Every group has one particular 1D irrep.
Identity.
That's the identity representation, which means every element is represented by the number 1. Okay? Every group has that. So, and since the number 1 is of course, that's a matrix which represents it. Remember the 1 by 1 matrix. But for a one-dimensional representation, the character and the number are the same. So you can immediately write down the characters. So I'm building up what is called the character table for this group. Okay. So one row complete. What about this column? Anybody tell me what this column will be like? Remember, this is the characters for the identity class or identity element, because the class only contains one element. What should this be? What is the character for the identity? We saw this just a while ago. What represents the identity in any vector space?
6.
No, what represents the identity?
And no change. It should be the same.
No, yeah, but
Zero.
what matrix represents the identity? The identity does no change, so it doesn't change any of the basis vectors. So which matrix represents that?
Identity matrix.
Yeah. So,
I didn't.
was the trace of that?
Dimension of the space.
Dimension of the space.
Dimension of the space,
Yeah.
which is the dimension of the irrep. This is d alpha. So, right? This column is immediate. Now we have to work a bit harder to get the other 4 elements here, but the work is pretty simple. Let me just point out one thing. If for 1D representations, this is for 1D representations only, the characters are the same as the representations, right? So what do representations do? They obey the group structure. So what do you know about chi-A times chi-A? Can you tell me that? Chi-A is the same as dA, right? In 1D, where D are the representation matrices. But what is this? D of?
D of A.
D of A. Actually,
No, what
A
is
square
D of A
equal to
square? What is A square?
A square is equal to A.
No, A square is not A. A square cannot be A. In a group, that's impossible unless A is E. Right? If A square is A, then you cancel and you get A is E.
Oh, okay.
A square should be E.
A square is E. Right? Is that okay?
Yes, it's okay.
And so that's 1, of course. In a 1D representation, this is always 1. So it's chi-A is a number whose square is 1. So what are the possible values?
Chi-A should be 1.
No, what are the possible values if a number squares to 1? Well, this is actually not about chi-A alone, it's also about chi-B and chi-C. But what are the possible
Plus
values?
minus 1.
Plus minus 1. Right, plus minus 1. But the important thing is, well, what about chi-D? Can you make a statement about chi-D? D is a 120 degree rotation. So what statement can you make about chi-D? If you repeat a rotation once, or if you do D times D, do you get the identity?
It will be chi-D into chi-D into chi-D, 3 times multiplication.
Chi-D cube must be 1, right? Again, this is true only for the 1D representations, because D cube is E. D is an order 3 element for the question that was asked at the beginning of today's session. A, B, C have order 2, D and F have order 3. But what does that tell you about chi-D? It tells you that chi-D is one of the 3 cube roots of identity, right?
Yeah, omega square.
Yeah, but now unfortunately we have way too many choices. We have 2 choices plus 1 minus 1 for this and 3 choices for this. So that would have given us 6 possible choices, but we have only 2 1D irreps, right? But you have more than just this. You have chi-A times chi-B. How much is that? That's chi of AB, right? But what is AB? 2 reflections, one after the other. What is that? Even if you don't remember the multiplication table for this particular group, I don't expect you to remember that. But I do expect all of you to know this simple geometric fact. If you reflect about 2 lines, two different lines, what is the net result?
It's a rotation.
It's a rotation. So can you tell me how much is the angle of rotation?
Half of the angle between the lines, I think.
Actually, it's just the other way around.
Oh, it's twice.
If you reflect here once and then reflect here, of course, this point goes all the way from here to here, right?
It is twice.
That's actually twice the angle of rotation, twice the angle between the plates. Okay, but important point is it's one of the rotations, which means it has to be either D or F, right? But what do you know about chi A and chi B? What did you learn a while ago about chi A and chi B?
They should be same.
They should
Because
be?
they belong to same. Same.
They belong to the same class, so they must be the same. So they're either both +1 or both -1. And what that means is, I don't care whether this chi is +1 or -1, this chi has to be +1. Right? Because it's a product of two +1s or two -1s. And so the other irrep here is just this. Okay, how can you find out the last irrep? I will just quickly tell you how the basic idea. The basic idea is that this vector 2AB must be orthogonal to this vector and this vector. But the rule is, remember, if you're just taking the numbers as it is, you have to weight by the number of elements in the class. So 2 times 1. So the orthogonality is not 2 times 1 plus 1 times A. So plus A times 1 plus B times 1 is 0. The orthogonality is 2 times 1 plus twice A times 1 plus 3 times B times 1 is 0. Right? Because there are 2 elements here and 3 elements here. Is that okay? So what you end up with is 2A plus 3B equals -2. Is that okay? And you also get 2A minus 3B equals -2. That is, this has to be orthogonal not only to this vector, but also to this vector. Right? All character vectors are orthogonal. Orthogonal in the sense of this inner product. Yeah? Any questions?
What is the last row E? I mean 2AB.
Last row?
I mean 2A.
No, I need to find out what A and B are. I'm just trying to tell you how to find them out. These are the characters of the 2D irrep. I'm just asking, how would you find out the characters of the 2D irrep?
Okay.
How you would find them out is just, there are many ways of doing it. I'm just showing you one of the most simple-minded ways. You just assume that they are A and B, some numbers, right? And then you just say, okay, this vector made by with 2, A, B must be orthogonal to 1, 1, 1. So I must get 1, which is the number of elements in the class, into 1 times 2. So 1 times 2 with this 1, which is being just the number of elements, plus 2, the number of elements in this class, times 1 times A, plus 3, number of elements in the third class, times 1 times B. This must be 0. So that's the orthogonality relation between this row and this row. If you use it between this row and this row, you get 1 times 2 plus 2 times 1 times A plus 3 times -1 times B equals 0. So can anybody tell me what these numbers are?
It will be -1 and 0. Then.
They have to be -1 and 0. It's very easy to solve these equations. There are other ways of finding out these answers, but there are many rather nice ways which you can put into a computer and directly find out. But I'm not going to go into the details of those techniques. But the basic idea is the character table can be built up this way.
Sir, but is it okay to get a 0 over there? Because that means that you have a non-trivial kernel. Right?
Really? Why?
Because if we have a 0, then it will be mapping.
What is 0 here?
0 is the function acting on the. It's the
No.
map acting on the.
Yeah, what is this map?
It's the null map
No.
acting on the vector space.
Is
Right?
This 0 is simply the character of the matrix, right? That's a trace of the matrix.
Okay, my mistake, yes.
Okay, if you would have been right in the sense that if it had been one of the 1D representations and you had a 0 somewhere, that would be disaster. Because for a 1D representation, the character is the same as the number. Of course, you are going to insist that all the matrices which represent group elements have to be invertible. Simply because you have this one very important result, dg inverse is d of g inverse. Right? So every matrix has to have an inverse. Because every group element has to have a corresponding d. Matrices have to be invertible, but traceless matrices are perfectly invertible. In fact, there are plenty of examples, right? All the sigma matrices and so on. Okay?
Yes, sir. I forgot we were talking about the characters.
These are characters. We are building up the character table. Okay. Now that we have the character table, can you? What good is it? Well, let's say we have found out right now the character table. Let me get rid of all this extra stuff. And now let us ask ourselves the question, can we use this to find out useful information? Well, we did something like this yesterday when we talked about molecular vibrations. So let me quickly remind you of that, and let me quickly talk about a case where this particular character table will be relevant. Of course, this is not the set of all symmetries of a square, right? This is a set of all symmetries of an equilateral triangle. So this will be relevant for a triangular molecule, let's say. If you had a molecule which was shaped like an equilateral triangle, and then we would be talking about 3 different displacements for 3 corners. Sorry, two independent displacements, because we are still talking of 2-dimensional situations. So there will be a 6-dimensional vector space here. And now quickly we would, so the point is set of all displacements of the atoms will give me a 6-dimensional representation of S3. Now, is this representation reducible or irreducible? Can anybody tell me that? That might sound like another stupid question. I've not even told you what the representation is. I've just told you it's 6-dimensional. But can you tell me whether it's reducible or irreducible just based on that? Yes? No? Maybe? You might say that there's too little information. You may have to work out the representation first. I'm just asking, is this reducible? I'm not even asking what the reduction is. Can anybody tell me whether this is reducible? Remember, this is a representation of the group S3 that we are talking about. Symmetry group of the equilateral triangle. And the hint to this is the answer is trivial. You should be able to tell me this without any thought whatsoever. And is
Reducible?
this, yeah? Tell me.
It
Yes,
should be reducible because the
It should be
dimension is 6.
reducible.
It is what?
Sorry, it should be reducible.
Why?
Because you said that it is a 6 dimension. So the dimension is
it is 6 dimension because there are 6 displacements.
1, 1. Yeah, 1, 1. Yeah.
Yeah, the point is we have
1, 2.
already figured out that we have 3 reps and we know the dimensions, right? They are 1, 1, 2, right? So it's trivial that a 6-dimensional representation has to be reducible because 1, 1, 2, of course, none of them is 6. The question now is how many times these 1, 1, 2 representations occur in this. Okay. Well, how do we figure that out? We need to find out the character for this representation. Now, the character for this representation is very easy to find out actually. Character for the identity, what will that be? For our representation, what will the character of the identity be?
6.
6.
Yeah, has to be, right? It's the dimensionality of the representation always. Okay, what about A? Remember, you don't have to find out the character for A, B, C separately. Only A will do. A is reflection along this line. And all you do is ask what happens to the basis vectors under reflection. And not only that, you just want the character, right? You just want the diagonal contributions.
It will be 0.
Why?
Because all the upward pointing basis vectors are unchanged, but all the horizontal ones are flipped.
Well, actually, you are almost right, but not quite. You don't even have to look at this one and this one. Because these two will flip over anyway, right? So this vector on reflection will not be this vector any longer. This will be this one.
Oh, okay. So only the top one will get
Only
one.
the top one will contribute. And for that, of course, you're right that E1, this horizontal one will flip. So E1 will become minus E1, E2 will become E2. So we'll get a total of 0. So you get 0 from this. Okay? And what about this one? When you rotate, what happens when you rotate? To 120 degrees. Yes? Any ideas?
It should be 0 as nothing points in the original.
Yeah, it has to be 0 because every point moves, right? So E1 will become a combination of these two vectors, but there will be no contribution to E1, right? Okay? So we have got these characters. But now that we have these characters, can you tell me how many times each irrep occurs?
It would only the.
You can of course use the M alpha formula, but you don't need to because you've already seen this once. This representation is not the regular representation, but it has the same characters as the regular representation, right? Mod G 0 0. Is it okay?
It will be 1 1 and 2.
It has to be 1 1 and 2. This has to come once. This has to come once. This has to come twice. Okay. Now that actually has a huge amount of impact on what are the possible normal modes and what kind of frequencies you can have. This actually is this one is a pretty simple problem where you don't even need the full group theory to figure the whole thing out. But let me just wind up today. Next day we are going to talk about how to actually find out the normal modes using this precisely, and what kind of degeneracies you can talk about just from this information. But let me just ask you one thing today. One of the normal modes has to be, so this 1 1 2 essentially, that this two-dimensional irrep actually occurs twice. Okay. What we need to talk about is the one-dimensional representation. For example, this one. This will correspond to a particular kind of vibration. It will not mix with any other vibrations because under symmetry group it does not go to any one of the others. So this will be a normal mode on its own. I will make this more precise next day. But this one is, what does it mean? It means that this is a kind of mode of vibration which will not change. That's what the 1 1 and 1 mean. This will not change when you carry out either the identity. Of course, for the identity nothing changes, that's rather trivial, or D or F or A or B or C. It will simply not change. So can you think of a kind of molecular vibration which is such, some mode of vibration which is such that when you reflect along the line A, it will not change. When you rotate through 120, it will not change, and so on. What kind of specific vibration are we talking about? So tomorrow we will.
They translate along the same axis together.
Yeah, but if you okay, you mean if they say translate along what? Say the x-axis.
Yes, same amount of translation.
But is this going to be the identity? Is this going to follow the identity representation? If you apply E on this, of course it will not change. But if you apply A on this, will this not change?
Okay, it should change.
It will change, right?
Yes.
It will flip over. If you apply B on this, it will sort of turn through by 60 degrees or something. So this definitely is not that particular mode, not the eigen mode corresponding to the identity representation. Tomorrow I'm going to tell you the formal way of finding out that mode just from the character table, and not just from the character table, but from the group irreducible representation matrices, and also tell you how this actually impacts on the eigenfrequencies and so on. But this particular one, it should be easy enough to guess. Think of a mode of vibration. Think of basically taking a film of the molecule as it is vibrating, and the film is such that whether you do A on it, B on it, C on it, D or F on it, you will not be able to tell the difference. Here you can see that a translation is a normal mode. It's a zero frequency normal mode, no restoring force whatsoever. But it's definitely not something which is going to transform according to the identity representation. It will change when you carry out various, it will still be a translation, but it will be a different translation if you carry out various operations. Any guesses? The guess actually, in this case, the guess should be pretty easy to make actually. So let's say, if I just imagine for the time being, this atom is going like this. Remember, you want it to be symmetric under A. So this particular atom has no option, it has to move this way. Right? Identity means it will not change when you reflect along any one of the ABC. So this atom has to move like this. Right? Because if it had a component along the x-axis, that would have flipped over. What does it tell you about motion of this atom and this atom?
They can't move because
they can't move at all. Are you sure? Because then the system will not be symmetric, and this will be symmetric under A definitely. But if it doesn't move at all, it will not be symmetric under a 180 rotation, right? Even the fact that it has to be symmetric under a 180 rotation should immediately tell you what the answer is.
It should be vibrating along B and C axis.
So basically the three atoms should be moving along the medians. But now can anybody, of course it doesn't mean that it's going to be moving out only. This is just a direction of motion. They can also be moving in. But can anybody tell me, now describe what should this motion be like?
Like breathing mode, it's like all moving away.
Is the breathing mode. Is the entire triangle expands and contracts. So the triangle becomes a bigger triangle, then it comes back to a smaller triangle. Okay, my drawing skills will be defeated here, but basically the triangle expands to a bigger size, then it contracts to a smaller size and keeps on doing that. That's one eigen mode. In this case, this particular eigen mode is easy to identify just by looking at the picture. The other ones may not be that easy to identify. But okay, how would you identify them, or how would you figure them out just by using group theory? That will be the final topic of the last lecture. That and what does this tell you about the frequencies? I will try to talk a bit about continuous groups as well, because I've been promising that, but I have got nowhere close to that. But while we are at it, just before I wrap up today, the final question. Can anybody tell me what kind of motion does this represent? If this atom moves this way, perpendicular to the median, this also moves perpendicular to the median, this also moves perpendicular to the median. What kind of motion are we talking about for the triangle?
rotation.
That's the rotation. That's a clockwise rotation, right? If the if the molecule were to spin along the perpendicular axis, that's what it would look like. But what representation does this rotation belong to? Just check. If you did identity, of course it will not change. If you did A, what would happen? So I'm going to use green to draw the result after A. This
It would,
will
it
of
would
course
become
move this way.
anti-clockwise.
This will move.
Clockwise rotation become
This
anti-clockwise.
will actually go here and move this way. And this one will go here and move this way. So basically the rotation reverses. So you get a minus sign. Clockwise becomes anti-clockwise, but the important thing is you pick up a minus sign. So under reflection A, it picks up a minus sign. It's pretty easy to see that under B and C also it picks up a minus sign. Okay. What about under a rotation? If I were to rotate about 120 degrees, what will happen?
It won't pick up anything.
Then this will move here. It will actually, this arrow will become this arrow. This arrow will become this arrow, right? This one will become this one. So this is a situation where when you do identity, it stays the same. Of course, that's trivial. You do A, B, or C, it changes, picks up a minus sign. Okay, but remember, notice one thing. This is a 1D. This ultimately is a 1D invariance of space because all it does is either pick up a sign or not pick up a sign. It does not take contributions from anything else. And if you do D and F, it stays 1. So which irrep is this? It's this one, right? Remember, among the 6 possible modes of motion, 2 have to be translations, 1 has to be a rotation. And you have only 3 vibrational modes. This identity representation corresponds to a vibrational mode. This second representation, which occurs only once, actually this is the rotational mode for this atom. This is the breathing mode for this atom. We still have 2 more vibrational degrees, but they must belong to either this or, well, there are only two copies left, right? This occurs in 2 copies. 2 of the vibrational modes will be sitting in one of those irreps, and the other irrep, other 2-dimensional irrep, will have what? Guesses? You just saw a while ago, the moment you say translation, that was the first choice, right? The translation was not invariant under the group. Actually, it doesn't stay, it doesn't pick up a minus sign, it doesn't stay in the same direction. Under A, it picks up a minus sign, but under B, it becomes something like this. Right? Under this reflection. This vector goes here and points this way. This vector goes here and points that way. This vector points this way. So basically, it becomes a different mode altogether. Okay. So what we will show tomorrow is that the other 2 modes of vibration have to be degenerate with each other. So if you have a triangular molecule, the symmetry dictates that there is one mode of vibration, which is a breathing mode. The other 2 modes, exactly what they look like, we will discuss that. And we will find out that they are actually degenerate modes. Okay? All this information actually can be found out just from the group theory. What cannot be found out from group theory is what will the frequencies be. That depends on the details of how strong the interactions are. But what can be found out from group theory is the basic structure of the eigenmodes, what kind of vibrations we will have, and if you throw in a bit of quantum mechanics, which of these modes will be infrared active in the spectrum, which modes will be Raman active, and all this. For that, of course, you have to throw in a bit of perturbation theory. There is quantum mechanical perturbation theory and how group theory speaks to that. That will be, okay, I'm not sure whether I will be able to cover that much in the next class, but I hope you have got a flavor of what we do, and next day we are going to wrap this up by showing you how to actually find out the modes formally. This one here, this is simple enough so that we could sort of do it by even guessing, but next day we will do it properly. Okay, any questions before I wrap this up?
So Professor Dasgupta, just one thing I'm a bit concerned about, probably you will have no time left for to discuss some league groups also.
Yeah, that's the problem. But I think there are other people who are talking about Dingin diagrams and Lie algebra zone.
That
Isn't that?
they will not be talking in the details. Means they probably will take it for granted. So if you can just possible, just give a very brief.
Maybe tomorrow I will just skip the rest of this, because this is something which people can also read in books. I will just talk about Lie groups tomorrow, perhaps. Just the basics.
Better. Yeah, just the basic, to the extent possible.
Okay, I will just talk about everybody knows the rotation group.
Yeah.
So I will just use the rotation group sort of as a template and describe things.
Okay, yeah, that would be better.
Yeah, but I will not be able to handle re-algebras, etc. But maybe in the discussion questions we will talk about that.
Yeah.
I'm sorry, I've gone way too slow. But
no, it's okay. You have covered enormous amount of stuff in such a short span of time, and people have interacted. That's a very good sign indeed. And I will look forward to your final lecture tomorrow.
Okay.
So
it's not a question, sir. Is it possible that some of the slides of the first 2-3 lectures you can share with us?
I will just correct them. There were some typos. I'll correct them and send over.
Yeah, thank you very much, sir.
Okay, so let us stop here, and we reconvene again with another within almost 20 minutes time. Actually, maybe not more 20 minutes also, maybe within 15 minutes time. Sharply at 6 o'clock, Professor Frederick Scholes is going to talk. So be here